So thank you very much for having me here. As you all know, I'll be talking about recurrent and state space models. So feel free to ask questions in between. I'll try my best to answer them, and if I can't, then hopefully I'll point you in the right direction. So I'll start with talking about the motivation behind recent efforts to revive recurrent models. And for large part of today's talk, I'll describe how different architectures work and how they relate to each other. I'll primarily focus on the key ideas behind the development of certain prominent architectures at the risk of some oversimplification. But by the end of the talk, I hope you understand how linear RNNs or SSMs can be trained as long convolutional models, what are the differences between SSMs and linear RNNs, how linear transformers can be formulated as recurrent models, and depending on how much time I have at the end, I'll talk a bit about the strengths and limitations of these models with respect to transformers. Okay, so um, as you all know, transformers are kind of like the go-to model for building LLMs right now. Almost all LLMs are based on transformers, but one major drawback of transformers is that the computational complexity to process a sequence is quadratic with respect to the sequence length. And the inference cost is linear with respect to the sequence length, and that is for generating one token. So suppose I give you a sequence of length 1000, and you have to generate a token with a transformer. And then if I go from 1000 to a sequence of length 100,000, then your computational cost will increase by a factor of 100. And given how ubiquitous these models are nowadays, like LLMs are being deployed by many companies. So the inference cost or optimizing the inference speed has become a lot more important than it was 4 or 5 years ago. And recurrent models, on the other hand, so one major advantage of traditional recurrent models like even LSTMs or GRUs, where they're fast inference speed. So with a recurrent model, to generate one token for a given sequence, your computational cost is constant with respect to sequence length. And that's to generate one token. If you're given a sequence of length n, then to process the entire sequence, the cost is linear as opposed to quadratic for transformers. But to generate one token, the cost is linear because it only depends on the size of the hidden state and not the entire sequence. And this before prior to 2018 or 19, recurrent models like LSTM were kind of the standard architecture for processing language. But around 2018 or 19, transformers kind of supplanted these recurrent models. And a natural question that you might have is the kind of how did transformers sort of go to become this standard model for building LLMs rather than recurrent models? And there's no right answer for that, but there's two major reasons that yeah, I think are important. So one thing is that these prior traditional recurrent models like LSTMs or GRUs, they didn't scale well. So suppose if you take an off-the-shelf implementation of LSTM, let's say you take the official implementation of LSTMs in PyTorch, then you can try and train a model with 3 layers, and you'll see that it works reasonably well. But as you go from 3 layers to a model of with 10 layers or 20 layers, you will see that the training is rather unstable, and your loss wouldn't the loss curve wouldn't be how you would expect it to be. So they don't work well when you take like large scale models with 10 or 20 layers and with large width. And the other drawback is that, in contrast to transformers, you cannot train them in a parallel manner. So, given a sequence, you have to process it sequentially with a recurrent model like LSTM. You have to kind of process it one by one. So, even if on paper their computational complexity is linear as opposed to quadratic for transformers, but still in practice, because you can train transformer in a parallel manner, so they tend to be faster for training. And that was one of the primary motivations behind introducing transformers in the first place. Like when transformers was introduced, the main motivation or goal of the authors was to kind of develop an architecture which you can train end to end in a parallel manner. So even though it was for machine translation, you could of course easily use it for things like language modeling in the way that we do nowadays. So in the past 4 to 5 years, people have sort of tried different things to different ways to modify and improve the training efficiency as well as the scalability of recurrent models. And that's what we'll kind of go into today. And before we dive into that, I just wanted to quickly mention that these approaches that people have taken in the last 3-4 years, you can broadly characterize them into three categories. Like these approaches to develop sub-quadratic architectures, you can sort of see them in three categories. So one class of models, probably the most popular one, is linear RNNs or SSMs, and this includes models like Mamba, Esper, DSS. And then there's a class of models called long convolutional models, the most prominent one being the Haina model. And more recently, people have tried to come up with different kind of linear transformer variants like RetNet and Mamba 2. But one thing to keep in mind is that these classes are not disjoint, and most linear RNNs are also long convolutional models as well. So that's what we'll see why that is today. But the converse is not true. Like not all long convolutional models are linear RNNs. And also, linear transformers can be seen as linear RNNs as well, or as you can formulate them as recurrent model, and that's also something we'll see today. Okay, so I hope everyone here is familiar with the basic definition of RNNs or recurrent model, but I'll just quickly give a recap. So the most crucial thing about the unique factor of a recurrent model is that there's a hidden state, which we'll denote with HT here. It's a n-dimensional or d-dimensional vector. And a recurrent model processes an input sequence sequentially, one by one. So it gets each token step by step, and it updates the hidden state based on the previous hidden state and the new input xt. And typically how it's done is that you just simply apply a projection. So this A and B are your parameters, and they are typically some kind of matrices. You can think of them as square matrices for now. So you apply a projection over your previous hidden state, you apply a projection over your current input vector, you sum them up, and you apply some kind of nonlinearity. And then you compute the output by applying some kind of projection, or you can have any kind of like feed-forward network, and you can compute the output as a function of your current hidden state. And if this nonlinearity is, let's say, tan H, then you get your traditional Elman RNNs. So linear RNNs are pretty simple. There's nothing fancy. You simply get rid of this nonlinearity. And so essentially you have the same equation, but we have no nonlinearity right now. So it's just a projection over previous hidden state. So your currently your function to update the hidden state is a linear function of your previous hidden state and your current input. And so why do we care about linear RNN? So what do we get by removing the nonlinearity? If anything, we are sort of making the model weaker because we remove the nonlinearity. So now it can express less things or less functions than it could originally do. So the key idea is that once we remove the nonlinearity, we can sort of write the entire computation as a convolution, and we can do the entire computation in a parallel manner. And that's what we'll see now. And for this part, let's assume the input to be a scalar. So our input xt is a scalar. Our hidden state is an n-dimensional vector, and our parameter a is a n cross n matrix, and this b and c are vectors as well. And I'll just explain this with the input being a scalar just for simplicity, but the entire thing generalizes quite easily to the input being a vector. You can sort of do all of these computations in parallel. You can just broadcast them and do all of it in parallel for vector. Okay, so now what we'll do is we'll just simply apply these equations for a sequence of 4 inputs, let's say x0, x1, x2, and x3. And then we'll see how we can write them in the form of convolution. So now suppose our initial hidden state is a 0 vector, and our first input is x0. We just apply this equation. So our h0 will just be b times x0, and our output y0 will be c times b times x0. So it should be pretty clear, pretty straightforward, right? So, and then similarly for the next input x1, we'll just apply this equation again. So our hidden state h1 will be it would be ab times x0 plus b times x1, and the output, it's just C times that those terms. So this is what you get for y1. And similarly, you can try and do this yourself and convince yourself that the rest of the outputs y2 and y3 will be of this form. And now you can sort of see a pattern here. You can see that given a sequence of inputs, each output yi will have these terms where these inputs are multiplied with these values of the form c a to the power something times b, right? So suppose you're computing the ith output yi, then x0 will be multiplied by ca to the power I times b, and xi on the other side will be multiplied by cb, right? So you can actually do all of these computations separately in parallel. You do not need to compute y2 to before computing y3. And the interesting thing is you can write this entire computation of producing y0 to y3 as a convolution between this filter, and the filter has these values of the form cb, cab, and so on. So you have ca to the power something times b, and it's a convolution of this filter and the input sequence x0, x1 to x3. And if you compute this naively, you can just sort of write a loop, and you can compute all of these in this way. And you'll see that your computational cost will be, or the runtime will be quadratic with respect to the sequence length. But just because we can write this as a convolution, we can apply the fast Fourier transform algorithm, and then we can do all of this in n log n time instead of n square. Okay, so let's just look at this with another simple visual example. So let's say we are given these four inputs, x0, x1 to x3. And as I mentioned earlier, our kernel is this, just values of this form, ca to the power something times b. And now what we'll do is we'll just see how the convolution works. So because we have the convolution between k and x, so we first just reverse this kernel. So even though the kernel is written in this form, when you do convolution, you reverse this sequence and you slide it across the input. So for our first output, we are applying this filter, just the first part of the filter over the input. And then we just slide it by one step, and then we apply it, multiply it with the input. And then you can keep sliding it, and then you can compute the rest of the outputs. So yeah, so in this way, we can sort of, when we have linear RNNs, we can compute this output in this convolution form. And because the size of this filter, so this filter that you see here, because this is of the same size as the length of your sequence, so that's why it's called long convolution model. So if you're familiar with convolutional, like traditional convolution models for sequences, you typically have a fixed size short convolution model, let's say of width 3 or 4, and then you slide it across the sequence. But here, because the size of it is the same as the length of your sequence, is just called long convolutional models. So if anyone has any questions, then feel free to ask them. Okay, so yeah, just one thing to note here. So with recurrent models, if you just simply apply the update rule sequentially, like the update rule that you have here, then your computational cost will be linear. It will be O(n), but you will process the input sequentially one by one. And when we are doing all of this thing that that I described here, your cost increases from n to n log n. But the advantage is it's still now we can do all of this in parallel. So even though the cost on paper increases, but in practice it's faster because of uh, parallelism. Okay, so I mean, this is not something very fancy or new. People knew this approach for a long time. It's not something people came up with a few years ago. But the issue was if you just go and directly apply this, and you just have a simple linear RNN that I described, then it won't work well. So but what people found is that if you just mix this with some tricks from transformers, like if you have layer norms and residuals after your linear RNN block, and say if you have a feed-forward network after that, and that's how you create each of your layer, then that really helps with scalability. Like so instead of just having your linear RNN block, if you just add these things, then you can have many layers, and with even with a large number of layers, your model works quite well. And multiple works have actually found that this recipe works for pretty much any sequence mixer. And by sequence mixer, this is a term that people use in these SSM papers. It just means anything that processes sequence, or anything that operates across the sequence dimension. So your feed forward network, for instance, does not process or apply to across the sequence dimension. It just applies to one input vector. But say attention or RNN, they apply across the sequence dimension. And what people found is that you can apply this recipe with a non-residual or feed-forward network, and you can pretty much put any sequence mixer. Even if you add these things to LSTMs, then they help with the scalability, and you can train models with large depth. And yeah, so that's something that's pretty interesting. Yeah, and so then, you might be wondering, so what are state space models? So this is a term that is relatively new in the field of machine learning. Before 3, 4 years, this wasn't that common. And a natural question is, how are they different from RNNs, linear RNNs? And the answer is actually they are kind of a subset of RNNs, so they are pretty much the same as RNNs. The crucial difference lies in how the weights are parameterized in a state space model. So in the RNN that I described earlier, we had three parameters, A, B, C, which were matrices. And in SSMs, you kind of have the same parameters, A, B, C, but along with that, you have another parameter, delta. And for now, you can think of this delta parameter as a scalar. And you start with these other versions of AB, which I've denoted with A bar and B bar here. And in an SSM, your first step of computation is to compute these matrices A, B by something called a discretization step. But essentially, it doesn't matter. What you do is you first compute A as a function of your A bar and delta. So similar to an RNN, say in RNN, your A is a n cross n, a square matrix. A bar is also a square matrix, but and A is also a square matrix, but this A is just a function of this delta and A bar. So for instance, one common way, common approach that is used in many state space model papers is that your A is computed by exponentiating the product of delta and A bar. So essentially you multiply the scalar delta with A bar, and then you exponentiate all the elements, and that's how you get A. And once you compute A and B, your rest of the computations are exactly the same as an RNN. You use them to update your hidden state, and then you compute the output. And the reason, yeah, people do this is it just depends on what your background is and where you're coming from. So these SSMs are a concept from control theory, and usually they are continuous time systems. So your even this index t does not need to be a natural number or positive integer. It can be 0.5, 1.75, anything. And your first step, the step that I described, is something called discretization. And what people have found is that so it doesn't matter a lot if you have this discretization step or if you directly initialize and use it in the standard traditional RNN form, but people just choose to use the one that they are more familiar with. And this is how it's typically used for traditional state space model. There's one called diagonal state space model. In diagonal state space model, this parameter A, which is square matrix, it's say restricted to be a diagonal matrix. So that's one approach, and it leads to some benefits. And possibly the most prominent state space models in this line of work, the most recent and the popular one is the Mamba model that you might have heard of. And the key idea behind the Mamba model is pretty simple. So this is the equation that I showed you for simple linear RNN. And you can note here that no matter what the input is or at what time step you are in, you update the hidden state with the same transformation. So you apply this linear projection A over your previous hidden state and B over your current input vector. And that's how you update your hidden state HT. And the key idea that is implemented in Mamba is that you can have different transformations across different time steps. So your B and C, or even A, they need not be fixed, and you can change them depending on the input vector that you get at each time step. And this is something that people in this community which worked on state space models, multiple works, they noticed that if you allow these transformations B and C or other parameters to differ at different time step depending on the input, then the performance kind of increases quite consistently. And the Mamba paper, essentially, they integrate it neatly within their SSM framework, and they also provide like efficient implementation to train the model and so on. And typically, so your this BT and CT, so they are a function of input, but the way they are computed, it's very simple. It's when I say it's a function of input or something, most of the time it's a linear projection. So there's no fancy function or something. So you can just apply a linear projection over the input vector and get your parameter BT. And because Mamba is also a state space model, so even though I've written this simplified equation, so you first have this A bar and B bar, which are then discretized and so on, but that's not super important. The key idea is is the fact that these parameters are dependent on input and are not fixed across various time steps. Because I described a few of these architectures, and the natural question you might have is, why are they not widely adopted in practice? What's the current state of these models and so on? And yeah, at the moment, none of these models are very widely adopted. Mamba is to some degree being used in various research communities, even beyond modeling language, say particularly for biological data or even audio data and so on. And the primary reason they are not widely adopted is because the performance does not yet match transformers performance. So both in terms of perplexity and even performance on various downstream tasks. So they are relatively worse, and the gap is sort of non-trivial. So that is one factor, and towards the end, maybe I'll talk a bit more about it if I have time. And the other reason is that the current hardware and infrastructure is very well suited to transformers. So because transformer just has a lot of matrix multiplications, and say for example, these linear convolutional models or linear RNNs. So when you have convolution and you apply FFT, a lot of these operations are not as fast as on TPUs as say attention. And TPUs are also widely used in industry. And even apart from your hardware, people have kind of come up with many efficient implementations and kernels for transformers. So even though on paper you go from n square to n log n, but in practice you don't get that kind of speed up. But that I think is the secondary reason. If in terms of performance they would have matched transformers, people would have put a lot of effort to increase their efficiency and get it to work way better than transformers in terms of speed. So I think the first reason is kind of the main reason, but I'll talk more about it. Um, yeah, so that kind of concludes the first part. If anyone has any questions, then yeah, feel free to ask. Then I'll talk about some other things. So I'll just take a maybe quick pause here.
Hi, excuse me.
Yeah.
Yeah, can I ask a question? So you're saying like the performance is not as good. So I'm wondering like because like for the original like transformers, like the performance like obeys like those kind of scaling laws. Like do you know like Mamba like follow those kind of things as well? Like once you like put in like a lot more parameters, like the performance is going to be better. Is it like there's some kind of specific things that can improve the performance? That's my question. Yeah. Or just like it's just like not as good as the original transformers at all.
Yeah, I'm not sure if I understood the question correctly. But in terms of scaling laws, of course, the scaling laws work for both transformers and all kinds of these recurrent
I
models.
see.
So in the sense that, so as you scale them, if you take bigger and bigger Mamba model or any of these linear recurrent models that I described earlier, whether it's diagonal state space models or just simple linear recurrent models. So as you scale it up, your performance will increase, so it will improve. But suppose what I meant is if you took a 7B transformer and you took a 7B Mamba, then even though, and you can tune both of them as much as you want, but even then, in terms of perplexity, there could be a slight gap. So Mamba is slightly worse than transformers in terms of perplexity. That's what you'll probably observe, or that's what at least I have seen. But in terms of downstream tasks, when you look at various kind of extraction tasks and a lot of things that you use your LLMs for. So there, the performance is relatively worse for all these models. And even if, so that's true even if you take even bigger models. And one tricky part about these models is you do not see these differences at small scale. So if you train a 300 million parameter model and you compare it with a 300 million parameter Mamba or any other state space model, the difference is usually not that stark, because first of all, you can't test them on a lot of downstream tasks. You need to train a much bigger model to even do evals uh, on many benchmarks. So you can only sort of gauge something from the perplexity. So yeah, one tricky part for this line of work has been that you kind of get a signal at large scale, which is difficult to do. But yeah, even at large scale, there is a difference. So
Okay, I see. Thank you. Yeah.
okay, okay. So maybe I'll continue.
Yeah, I'll just relay the questions. There are a few questions from the students in the
Yeah,
class.
sure. Yeah. I can't hear anything. So hello.
So the question is like, what's the bottleneck in making FFTs faster? Is it dependent on like how the kernel implementation takes place, or I guess that was the point.
So your audio wasn't clear. So what are the bottlenecks for making what faster? Is
The FFT implementations faster. Is it really the kernel implementation that it depends on, or are there some other inherent properties? I guess.
Yeah, I think a large part of it is that you can, if somebody puts a lot of effort, they can write more efficient kernels and so on. So these FFTs are not inefficient on GPUs, but it's primarily that TPUs are not built for this. So TPUs are just built for matrix multiplications of bfloat 16 matrices, like with all elements in bfloat 16. As soon as you have any operations with complex numbers in TPUs, everything will slow down. So that's an issue with TPUs, and they have had this for a long time, and but they probably don't have a lot of incentive to fix that. Even there are some papers from Google's different research teams, and which involve like FFT or Fourier transforms. And even within those papers, they have mentioned that it just doesn't work well for them on TPUs. And on TPUs, they rather do the inefficient version of Fourier transform, where there's just matrix multiplication, because that's faster. But other than that, so apart from FFTs, let's say on other things as well, it's just that people have not put a lot of effort into optimizing stuff and hardware level and implementation level. So, but that's because there is no fixed architecture. Like, say for transformer, you have one architecture. Everyone wants to know that this is the one that's used. People can kind of optimize that. But for SSMs, right now, Mamba one is a prominent one. So Mamba, you do not have to train it as a long convolutional model, so it's trained in a different way because of the fact that you use different transformation at every step. But yeah, I think it's just because there's less incentive. Once you have a kind of like a prominent architecture which works well, then maybe people will put more effort. Any other question? Can you, or does that answer your question also?
Yeah, I think it did. Yeah, I'll just look for any other questions if someone has. Yeah, you can proceed.
Okay, so I'll continue, and so maybe you can ask questions after the second part. So yeah, in the second half, I'll talk about how you can sort of do, so how you can train linear transformers in the same way as you train vanilla transformers, which is very straightforward. But at the same time, we can do the inference in a recurrent manner. And sort of we'll build over that to see how you build on it to get RetNet and the Mamba 2 model. So I presume everyone here is familiar with the transformer architecture, or at least the attention mechanism in particular. So yeah, just recall that. So the attention block, it takes n vectors as input, is x1 to xn. So it takes n vectors as input, and it produces n vectors as output, which will denote z1 to zn, at least for the rest of the discussion. And what you do is, given these input vectors, x1 to xn, you first apply a set of projections, and you get 3 different vectors for each input vector. So given xi, you get query key value vectors. All of these are, let's say, d-dimensional vectors. And then you compute the inner products between the query vectors and the key vectors, which we'll denote with this Aij. And essentially, first you compute this n cross n matrix. If your sequence length is n, you create the n cross n matrix, which has all the dot products. And your output z, which has z1 to zn, you can sort of write it in this way. It is the softmax of over A, and say it's a row-wise softmax. And then you multiply it with the value matrix so that you get a weighted combination of the value vectors. And particularly in the case of language modeling, when we are using transformers as language model, we have this positional masking because we do not want the attention mechanism or transformer to attend over sequences beyond a particular length. Suppose we are processing a sequence up to length I, we do not want it to attend over tokens beyond length I at I plus 1 or higher, right? So what we do is we first compute this matrix A, which has all the dot products, and then we multiply it element wise with this mask matrix, which is a lower triangular matrix where the upper part has minus infinities, so that when you multiply these with the attention matrix, and because we are going to use softmax, we'll exponentiate them. And when we exponentiate them, then this minus infinity will turn to 0, right? So we multiply this mask matrix with the attention matrix A, and then we apply softmax. We get these values between that sum up to 1 in each row. And then we multiply this with the value matrix. So I hope everyone is clear about this. So this is just the basic definition of how attention works. So linear transformers or linear attention, it's pretty simple. There's nothing fancy. Similar to linear RNNs, we are going to get rid of the nonlinearity, which was softmax. And essentially what we have is we first compute the dot products, we'll apply a mask matrix, and we'll multiply it with the value matrix. And yeah, one simple change that we'll have to make is that our mask matrix now will contain zeros instead of minus infinities, because we are not going to exponentiate them later. And we want these dot products beyond a particular position to be 0. We want the weights to be 0, attention weights. So we directly multiply them with 0 because we're not going to exponentiate them. So if say today you want to implement a linear transformer and you want to train it, so you just have to make these two simple changes. So you just remove the softmax and you modify the mask matrix in this way, and you can essentially train this linear transformer in the same way that you train transformers. So it's everything is parallel while training. But at the same time, what we'll see now is that once we train the model to generate tokens, we can do it in a recurrent manner. Okay, so now let's see how each output is computed in the case of linear attention. Suppose we want to compute the ith output, which is Zi. So what we'll do is we'll take the ith query vector and we'll take the inner product with the first I key vectors, right? And that's how we'll get I attention weights, which will be the dot products. So between Qi K1, Qi K2, and so on. And then we'll multiply it with the first I value vectors, and we'll get a weighted sum of the first I value vectors, right? So let's look at a few examples. Let's say we want to compute the first output. It's very simple. We take the inner product between Q1 and K1, and we multiply it with V1, and we get output Z1. With Z2, the second output, we take the second query vector, Q2, we multiply it with K1, we take the inner product with K2 as well. These are the weights, and we then take the weighted sum of V1 and V2, right? And similarly for Z3 as well, we take the third query vector and multiply them with the key vectors up to the third key vector, and then sum the first three value vectors, right? So then you can sort of see a pattern here. So because, and the key thing to note here is that because matrix multiplication is associative, so that's why we can take this Q2 or Qi's out, and we can write this same computation. So this Z1 to Z3, we can write it in this way, right? So, and here you can see that the way we are computing the output is we multiply, computing the ith output Zi, we are taking the ith query vector Qi, and we are multiplying it with the cumulative sum of outer products of key value vectors, right? So suppose we're computing Z2, we take the second query vector, and we have these outer products of key value vectors. And yeah, one thing to note here is that once we are kind of switching this mode of computation, so earlier we had inner products of query and key vectors, but these ki, vi, so k1, v1 transpose, so these are outer products. So say k1 is a d-dimensional vector and v1 is a d-dimensional vector, then this k1, v1 transpose will be a d cross d matrix. So all these terms here of the form ki, vi transpose, so all of these are d cross d matrices, right? So now you can sort of see where I'm getting at. And so essentially, the basic idea is that when we compute the second output, let's say Z2, to compute the second output, we will compute the cumulative sum of K1 V1 and K2 V2. So these key value vectors. And so if we store that, if we store this sum, and then if we need to compute the third output Z3, then we do not need to perform all these computations. We can just add the final outer product and then multiply it with the current query vector, right? So that's kind of like the main idea behind this. And then now we can kind of write this as a recurrence. So say here we have a hidden state matrix. It's a D cross D matrix. So as opposed to the previous RNNs that we're looking at, so where we represented the hidden state as a D-dimensional vector. So here we'll represent it as a D cross D matrix, and we'll denote it as ST. And say our initial hidden state is a zero matrix. So update rule will be as follows. So when we process a sequence, so whenever we get an input vector, we'll update the hidden state by taking the previous hidden state and adding the new outer products of key value vectors. So this is our rule for updating the hidden state. And then to compute the output, we'll simply multiply the new query vector with the current hidden state. Right. So now let's say if we just apply these rules. So given a sequence of input, so if you just apply these equations, then you can see that the way your hidden states will look the following, and then you can compute the output by applying the last equation, and your output will look this way, which is exactly the same as the outputs in the previous slide. And this is kind of the main idea behind how you can write linear transformers or linear attention in the recurrent form. So I hope this is clear. So building over this, there was another architecture. It's called RetNet, and their idea was quite simple as well. So there are three changes in the architecture, but two of them are not kind of unique and are used in other architectures as well. The main change in the architecture over linear transformers is as follows. So what they kind of did was that instead of just adding the previous hidden state with the outer product of key value vectors, they first multiply the previous hidden state with a scalar gamma, and you then add it with the outer product of the key value vectors. And this was sort of motivated by some previous works in linear RNNs or SSMs, which observed that your SSMs were kind of implicitly applying some kind of exponential decay factor. And when you do this, when you multiply at every step, when you multiply the previous hidden state with gamma, you are sort of adding an exponential decay factor. Because suppose you are computing the 100th hidden state, S100, then you multiply the previous hidden state with gamma, S99. But when you multiply S99 with gamma, then you are multiplying S98 with gamma square, because each hidden state is recursively the previous hidden state plus an outer product. So as you go to higher time steps, the older hidden states will be multiplied by some powers of gamma. Right? Uh, so that's kind of the basic idea, and it actually helps improve the performance. So tomorrow, if you take an implementation of transformer, you can train a language model. You can then remove the softmax, train a linear transformer, and you'll see a drop in performance. You will see that the performance will decrease. And then if you make this change of having this decay factor or multiplying the scalar, you'll see that once you add this, then the performance will increase compared to a linear transformer. It will still be not as good as transformers, but this will lead to an increase in performance. And this is how you write it in the recurrent form, how you generate tokens with that. But you can also train the model. So you, in the same way as you train linear transformers or transformers. And the only thing that you have to change during training is this mask matrix. So you do everything in the same way that you do for linear transformers. But instead of having a mask matrix with ones and zeros, now your mask matrix will have different powers of gamma. So, and you can kind of check and verify yourself that this computation this is exactly leads to the same output as this recurrent form. So we saw this for linear transformers, but it's kind of easy to see how this works for RetNet as well. And here as well, the basic idea is you can train it in parallel in the same way as you train transformers or linear transformers, but you can do the generation in a recurrent manner. And then more recently, earlier this year, the Mamba 2 model came out, which is a generalization of the RetNet model. And if you kind of followed up to this point and you have understood the RetNet model, then it should be easy to follow how Mamba 2 works. And their idea itself is very simple. Their basic idea is that in RetNet, you have this gamma that you multiply with the previous hidden state at every step. And but this gamma is constant, no matter whether you are, no matter which token you are processing, or whether you are at 100 hidden 100 time step or 200 time step, your gamma will be the same. You will multiply gamma with your previous hidden state. But instead of that, the basic idea is that what if we allow gamma to depend on the input, and we allow it to change depending on what the input vector is at different time steps. So the main change in the Mamba 2 model is the scalar here, AT. So this equation here just follows the same notation as the Mamba 2 paper, but I'll just show you how it looks if we apply our older notation. So this is the equation for RetNet that we saw in the previous slide. So we have ST, which is our hidden state, and it's updated by gamma times ST minus 1 plus outer product of key value vectors. And this is the same equation for Mamba 2 with the same notation. And the only change here is that instead of gamma, we have AT, which is another scalar, and this AT with a subscript T to denote that it depends on the time step. So it essentially depends on the input vector. And yeah, so this sort of allows the model more degrees of freedom. So it allows more flexibility because now AT can be different at different time step. Your model can sort of express more functions compared to the RetNet model. So that's kind of the key idea behind Mamba 2. And similar to how I described linear transformers and RetNet, you can also kind of formulate Mamba 2 as a transformer model, a linear transform model, where you just have to change the mask matrix. So we have this matrix A, which has all the dot products, and our mask matrix now, instead of having 1 and powers of gamma, but because now gamma is not constant across time, so we'll have different products of AIs or ATs. So instead of gamma square, we have A2 times A1, and then instead of gamma cube, we have A3 times A2 times A1, and so on. So yeah, intuitively, it's easier to think of how Mamba 2 works based on how linear transformer works and how the recurrent form works. But yeah, one thing I want to mention is that you actually do not train Mamba 2 in this way. You do the inference exactly in this way that I've described in this recurrent form, but training Mamba 2 in this way is not efficient. And the primary reason is because creating this mask matrix is not easy. It's not, you can't create it efficiently. Because for RetNet or transformer or linear transformer, the mask matrix only has constants. So it's very easy to create it with NumPy, just broadcast it, and you have different powers of gamma. But with Mamba, because you have these different products, if you create it for, let's say, a sequence of length 8,000, so it takes quite a lot of time. And one of the main contribution of the Mamba 2 paper was to kind of provide an efficient algorithm to train the model. And so they basically observed that, like, if you write this computation in the form of a large matrix, then it has a certain structure. It belongs to a class of structured matrices, because of which you can apply certain kind of block decompositions. And they kind of so they propose like a chunked algorithm to train Mamba 2. So that algorithm in itself is a separate discussion. But I just want to mention that you do not train it this way, but this leads to the right output. So you are essentially performing the same computations, whether you write it this way or in the recurrent form or the other algorithm that they use to train the model. Okay, so that brings us to the end of these description of models. So yeah, before I end, I'll just maybe talk a bit about some intuitive differences between how these models work. So I'll just take a couple of minutes to do that. Yeah, so one thing is, like I mentioned earlier, so the reason they are not currently widely adopted is there is a non-trivial performance gap between all of these architectures that I described and transformers. So the good news is that compared to 3 years ago, the gap has been substantially reduced. But and maybe like in a year or in a few years, the gap will be almost null. But yeah, we'll see that. But on the other side, one promising thing is that many research groups from different parts of the world, what they have observed is that hybrid architectures seem to be working really well. And by hybrid architectures, what they mean is that if you, let's say, have a 20-layer model and you just have a few layers of standard transformer layers or standard attention, and then your rest of the model, like say 15 to 16 layers, um, you have some kind of linear RNN or SSM, then such a model is almost as good as transformers in terms of performance, but you get much faster inference with such models. Also, yeah, one other thing, if you might find it interesting, and I'll just talk briefly about it. So you might be interested, or you might wonder, like, what are the differences in the strengths and limitations of these models? So because both transformers and all these recurrent models, so you can see them as a computational model. So all of these are some form of computational models. They take some inputs, perform some computations, and they produce an output. And transformers and all the models that I described today, so you can categorize them as recurrent models, and they process inputs very differently, and that leads to different strengths and different limitations. So the main thing about transformers is that throughout the computation, they always maintain n vectors because they need that to perform attention, and they process the entire input in parallel. RNNs, on the other hand, so they have a fixed size memory vector. They can manipulate the memory vector based on the inputs at every step, but they must have everything in a fixed size vector. And this leads to some limitations for, let's say, RNNs, for example. So one issue with RNNs is that no matter what task they have to perform, they always have to compress all the information that they might require into a fixed size vector. And this makes it difficult for them to perform certain kind of associative recall tasks, which are very relevant to uh, performing downstream tasks as LLMs and so on. So for instance, I'll give you this one example. This is called multi-query associative recall, where you are given a sequence of keys and values. So here the letters are the keys and these numbers are the values. So you're given a sequence of key values followed by these keys again, and then you have to produce the associated values. And you can sort of see how this is very easy to do with attention. So suppose you get this query C, so you just have to attend over the right key, and then you have to produce the value 6. But for all these recurrent models, on the other hand, so they have to first compress all of this into a single hidden state, because then while performing this recall task, they have to use that same hidden state to retrieve the output. And this is sort of the intuition. And based off this intuition, there is enough like theoretical evidence to suggest that these are hard for recurrent models. People have empirically observed this on various synthetic tasks. And yeah, more interestingly, there's this paper, the second one, Zoology, which shows that this kind of modeling behavior is relevant to how models perform, relevant to language modeling in practice on natural language data. And so that's for RNNs. And for transformers, one thing people have found is that on various kind of algorithmic tasks that require modular counting, so transformers struggle. It's difficult for them to do those kind of tasks. And maybe the prominent one is parity. So parity is a very well-studied function in theoretical computer science. The function itself is very simple. Let's say it's a binary classification function. And given a string of bits, zeros and ones, the output is, let's say, 1 when the number of ones is odd, and the output is a -1 when the number of ones is even. So you just have to check whether the number of ones in a sequence is even or odd, and the zeros do not matter. And this is something which is very easy for recurrent models to do, because if you have a hidden state which you can update at every step, so take the hidden state, whenever you have a 0, you ignore it. Whenever you have a 1, whenever you encounter a 1, you just flip your hidden state from 1 to -1, or say -1 to 1. So whenever I see a 1, I flip my hidden state from 1 to -1. I encounter 1 again, I flip it from -1 to 1. And then at the end, no matter how long my input is, even if my input has billion is of length 1 billion or more, with just a very small hidden state, I can perform this very easily. But transformers, on the other hand, because they have to process this entire thing in parallel, and they do not have a hidden state, they do not have a state vector, so they have to kind of compute this based on a weighted combination of these input tokens. And that kind of like is the intuition behind why this is difficult. And similarly for this task as well, both there's theory and experiments to suggest that this is hard for transformers. But the impact on, say, downstream performance or LLM performance or just practical task, the impact of this is unclear. We don't know whether this matters or not. But yeah, but this is a simple example. There are more tasks which kind of yeah have similar kind of modeling behavior. Yeah, so that's it. Yeah, thank you very much for listening. Yeah.